You've seen the incredible images, you've read the poetry, you've probably even talked to a chatbot. Generative AI is, well, it's everywhere. But how does it actually work? I mean, really, under the hood. Well, today we're going to pull back that curtain and look at the core concepts that are powering this whole revolution. Let's get right into it. First up, we're going to start with the absolute basics. What does generative even mean? Then we'll meet the key architects, the different types of models out there. After that, we dive into the big one, the game-changing transformer. Then we'll see how we try to make these things helpful and safe. And finally, we'll check out the clever engineering tricks that make all this power practical for you and me. All right, so let's start at square one. What is generative AI? At its heart, it's pretty simple. It's about teaching a machine to go beyond just recognizing patterns. Looking at a million photos of cats and saying, that's a cat. Instead, it learns those patterns so deeply that it can create something brand new, a new image, a new song, a new story that fits those same patterns. It's that jump from just recognizing to actually creating. Now, this whole creating thing comes in two main flavors. On one hand, you have unconditional generation. This is like telling an artist, hey, just paint something. You'll get something cool for sure, but you have zero control over it. But then there's conditional generation, and this is where all the excitement is right now. This is like telling the artist, paint me a picture of a fox wearing a top hat in the style of Van Gogh. You're giving it a condition, a prompt, to guide what it creates. So you might be wondering, where do these new creations actually come from? Does the AI just pull them out of thin air? Well, kind of. They come from a place called the latent space. And the best way to think about this is as the model's own internal map of ideas. Instead of memorizing every single picture of a cat it's ever seen, it learns the concept of catness, the essential features, and organizes those ideas in this super compressed, abstract space. And this analogy of an artist's palette is just perfect. Imagine the latent space has concepts like furry, pointy ears, whiskers, and cat. The model can just pick a point in that space that mixes those ideas together, and its decoder translates that abstract concept into a totally new picture of a cat that has never, ever existed before. It's amazing.
Okay, so models use a latent space to generate things. But how do they learn to build and navigate that space in the first place? Well, it turns out there are a few major schools of thought on this, a few different families of generative models, each with its own strategy. Let's meet the three main architects.
This table breaks down the different philosophies so well. First, you've got GANs. This is a constant cat and mouse game. One AI, the forger, creates fakes, and another AI, the detective, tries to spot them. They both get better and better in this endless battle. Then you have VAEs, which are way more methodical, like an architect. They learn to create a perfect compressed blueprint of something so they can build new, similar versions from it. And then you have diffusion models, which power a lot of the best image generators today. These are like sculptors who start with a block of pure random noise and slowly, carefully chip away at it until a perfect image emerges. So for a long time, progress in AI was, well, it was steady. Things were getting better. But then in 2017, a research paper dropped that introduced a new architecture that didn't just move the goalposts. It basically invented a whole new sport, especially for language. This was the transformer. To really get why this was such a seismic shift, you have to know what came before. Older models, like RNNs, read a sentence just like you would, one word at a time, in a line. And the problem is, by the time they got to the end of a long paragraph, they'd kind of forgotten what was said at the beginning. The transformer's big idea was to just throw that out. It said, why go in a line? Let's look at every single word in the sentence at the exact same time. And the secret sauce that makes this possible is a mechanism called self-attention. If the transformer is a superhero, this is its superpower. It's what allows the model to weigh the importance of every other word when it's trying to understand a single word. This is how it knows that the word bank in riverbank means something completely different than the bank in I'm going to the bank. It gets the context. And it works using this really clever system called query key value. Think of it like this. For every single word, it creates a query, which is like the word asking a question. Hey, who here is relevant to me? At the same time, every other word produces a key, which is like a label that says, here's what I'm about. The model then plays matchmaker, finds the most relevant keys for that query, and then pulls the value, the actual juicy information from those words. I absolutely love this analogy. It really is like a networking event for words. Instead of passing messages down a line and hoping the meaning doesn't get garbled, Every word can instantly talk to every other word in the room, no matter how far apart they are. It creates this incredibly deep, rich understanding of context, and it was a total game changer. Okay, so we've got this unbelievably powerful engine now with the transformer, but, a powerful engine is one thing. A powerful engine with a steering wheel and brakes that you can actually control, that's a whole other challenge. And it's an incredibly important one, making sure these models are helpful, harmless, and aligned with what we want them to do. The main technique we use for this today has a bit of a mouthful of a name: reinforcement learning from human feedback, or just RLHF for short. This is basically the finishing school for a raw AI model. It's the process that turns it from something that can just predict the next word into a helpful assistant that can follow your instructions and avoid harmful topics. RLHF is this really cool three-step process. First, you just give the model a bunch of high-quality examples written by humans to teach it the basics. Step 2 is the clever part. You have humans look at several different AI-generated answers and rank them from best to worst. You use this data to train a separate AI, called a reward model, to act as a judge of what humans like. And finally, in step 3, you fine-tune the main AI with one simple goal: generate answers that get the highest possible score from that judge. But even with all this careful alignment, these models still have a pretty big problem, something we call hallucination. This is when the model says something that sounds perfectly reasonable and confident, but it's just completely wrong. It's confidently making stuff up. And it's important to remember, it's not trying to lie. It's just a pattern-matching machine, and sometimes the most statistically likely pattern is, well, fiction. So why does this happen? Well, there are a few main culprits. The model is literally designed to be a confident guesser. Its training data was scraped from the internet, which is full of, let's say, mixed quality information. Its knowledge is also frozen in time from when it was trained. And if you ask it a vague question, it's programmed to fill in the blanks, even if it has to invent those details itself. All right, so we've got these incredibly powerful, aligned, but sometimes flawed models. The last piece of this puzzle is all about the practical side. How do we take these absolute behemoths with hundreds of billions of parameters and make them something that can actually run on your phone or your laptop? This is where the engineering toolkit comes in. First up, we have LoRa. Think about this. Fully retraining one of these giant models can cost millions of dollars. It's just not practical. LoRa is a brilliant workaround. It freezes the massive base model and just trains these tiny little adapter layers that you plug in on top. It means you can efficiently specialize a model for a new task for a tiny fraction of the cost. Next is a technique called quantization. The simplest way to think about this is like compressing a huge, high-resolution photo into a smaller JPEG file. It takes all the super precise numbers that make up the model's brain and just rounds them off to simpler, smaller numbers. You lose a tiny bit of precision, but the model becomes dramatically smaller and faster. And the payoff here is huge. As you can see, quantization just crushes it on all fronts. It drastically reduces the memory the model needs, it speeds up how fast it can generate an answer, and it lowers how much power it uses. This is one of the key tricks that makes powerful AI accessible to all of us, not just giant tech companies. And another really powerful idea is called mixture of experts, or MOE. Instead of building one massive, monolithic brain that has to know everything, you build a model that's made of many smaller, specialized expert networks. Maybe one is a history expert, one's a coding expert, one's a poetry expert. Then a smart little gating network acts like a router, sending your request to only the few experts best suited for that specific job. And what this allows for is incredible efficiency at a massive scale. It lets developers build models with, say, 1 trillion parameters, but for any single question you ask, it only activates a tiny fraction of them. It's like having a whole library of knowledge at your disposal, but only needing to pull 2 or 3 of the most relevant books off the shelf to get your answer. So there you have it. From the foundational concept of the latent space to the revolutionary transformer architecture, the alignment that makes them usable, and the practical engineering toolkit that brings it all to life, we now have the ability to build, align, and scale these systems in ways we could have only dreamed of just a few years ago. And that leaves us all with the biggest question of all. Now what do we do with it?